second session in morning. The next talk is Philipp Schneeweiss. I hope I pronounced your name correctly.
Schneeweiss.
Schneeweiss. And he will be talking about optical isolation.
Yeah, thank you. And thanks also to the organizers for setting up this meeting. I'm working in Vienna in the group of Arno Rauschenbeutel. And there we couple cold atoms to micro and nanophotonic structures. And today I want to tell you about the effects on the light, which is coming up due to this confinement of the light. All right, so first a few words about the general motivation. So why do we want to confine the light? In the first place, we want to confine it in space and also in time in order to just drastically increase the interaction between single emitters and single photons. And moreover, beyond just quantitatively increasing it, we also see new effects arising as soon as the light is strongly confined. And then we can use these new effects in order to develop new protocols for the interaction of photons and atoms, or photons and other photons via these atoms. And we already have heard about a few different systems which are used to explore this physics. And here I just give a quick overview about a few systems where single atoms are coupled to optical photons in non-photonic structures. So this was the talk we just heard about before, and that was the first one of this morning. Then there's also a lot of work about like whispering gallery mode resonators. For example, here these spherical resonators, which are explored by Barak Dayan. Or, for example, here atoms are coupled to surface waveguides. That's work of the group by Ed Heinz in London. And the systems that we are using in Vienna are shown here. So one is tapered fibers. And one example of these are shown here. So it's a standard fiber is tapered down to a narrow diameter, which is about 500 nanometers. And the length of that can be several centimeters. And we have developed this tapering process quite far yet, such that we get more than 99% of the light from here to here. And a second aspect of the narrow diameter here is that actually large parts of the optical power are propagating as an evanescent field. And this allows us to bring atoms close to this evanescent field and couple it relatively efficiently. Jeff Kimball already pointed out, so efficiently in our case means it's about 5% of the light which is propagating in the fibers absorbed by a single atom. So that's one of the systems we are working with. And second system is a special type of whispering gallery mode resonator shown here on the right. So we call this a bottle resonator. And on this we can excite modes which are traveling around this bottle. We get very high Q factors of about 10 to the 8 in that system. And so relatively small mode volume combined with the high Q factor allows us to enter the cavity-quiddy strong coupling regime for a single atom. And a special aspect of that bottle resonator is that it is easily tunable. So by pulling on the ends of the resonator, we can tune the atomic resonance over more than one free spectral range. So no matter where the atomic resonance is, we can always tune the resonator into resonance with the atoms. So that are our two systems, and now I'm going to tell you what we did in the last, in the recent months using these systems. So here's a short outline of the talk. So first I will tell you about chiral photons and their interaction with matter. And secondly, I will talk about an application of these chiral photons. And this application will be an optical isolator that we recently realized. And finally, I will give a short outlook and summary. All right, so let's start with an introduction. And this introduction will be, first of all, about how to describe light, especially in confined dimensions. So if you first think about light, you think, okay, it's a transversely polarized wave. That means the electric field will oscillate perpendicular to the direction of propagation. But that's not true anymore if light is strongly confined. And I think Peter Loder maybe already mentioned that to some extent. Here I want to go a bit more into detail what is happening with the polarizations in these strongly confined light fields. And as an example, we take a strongly focused Gaussian beam, which is shown here, where the waist of the beam is on the order of lambda. And in that case, if you look at the polarizations, so we sent in this light, let's say, from left to right, and this is supposed to be linearly polarized. And now we want to have a close look at the polarizations in the focus. And first of all, there's the expected transverse component in the first place, which oscillates perpendicular to the axis of propagation, to the vector of propagation. And in addition to that, there's a second important polarization component, which is a bit less familiar, and that is actually a longitudinal polarization component of the electric field, which is oscillating in parallel to the direction of propagation. And so there are a few important things to know about this polarization component. One thing is it is 90 degrees out of phase with respect to the transverse components. And secondly, this longitudinal component gets significant as soon as you confine the light transversely on the order of lambda. This is summarized in that formula here. So that is a transverse gradient. And as soon as this is on the order of the wavelength, then there will be significant longitudinal component. And this is pi half out of phase with respect to the transverse components. So the consequence of these properties of that EZ component here are the following. So if I look at this particular position in the beam, the polarization will be actually circularly polarized, so the electric field vector will turn. And what is very unfamiliar is that the photon spin, which is associated with these light fields, is actually perpendicular to the k vector. So, I mean, for an ordinary circularly polarized light field, which is propagating in free space, these two vectors are always either parallel or anti-parallel. In this case, it's a transverse spin, which we are having for these strongly confined light fields. Okay, so the next aspect we want to look at is what happens if I send the light field not only in one direction, but if I reverse the direction of propagation. So in the lower picture, the beam is propagating from the right to the left. And what happens then is that then this circular polarization is turned around. So I get a minus sign here. So the important aspect to keep in mind here is that for nanophotonic light fields, there can be an inherent link between the local polarization and the propagation direction. And this aspect is, we call that the photons that are propagating in this light field obtain a chiral character. All right, so this physics is also present in our optical nanofibers, and so it's actually quite pronounced. So quantitatively speaking, the overlap of the polarization, like slightly above the fiber, with, for example, sigma minus is already 92%, so quite high. So it's not just a small side effect; it's really significant. And one small difference to these glide plane waveguides that have been described in photonic crystals is that in these systems here, the light is really everywhere along this nanofiber sigma plus or sigma minus polarized. So there's no periodicity, it's just everywhere having exactly this polarization. Okay, so we are aware of this polarization properties of the nanofiber guided modes now. And next thing we wanted to do now is to probe this mode structure and to see and observe effects which are arising from this mode structure. And for that purpose, what we did is, so we took out one of these optical nanofibers, and we brought a cold cesium atom close to the nanofiber, and this atom is trapped in a nanofiber-based dipole trap, which is realized using one blue and one red-tuned light field, which is propagating in the fiber. And the overall trapping potential we have already seen in other talks. So in a nutshell, it's important to know that there's two arrays of trapping sites, where in each site there can be at most one atom due to this collisional blockade effect. So the atoms are nicely isolated from each other and can be treated individually. And now we use these trapped atoms in the vicinity of the nanofiber surface to probe this chiral mode structure that I just explained before. To do so, we illuminate the atoms from the side, and then we observe what is emitted into the fiber. So here's the experiment. So we put the atoms, in this case, in the measurement I'm going to show, about 5 atoms close to the nanofiber surface, and then we put 2 SPCMs, one on the left end and one on the right end of the fiber. And so what do we expect now? So first, here's a little level scheme of cesium. That is the F equals 4 hyperfine manifold of the atomic ground state, and that's a 6p3½ excited state, so the excited state that I'm addressing is the V2 line. And if we, for example, prepare the atom first here and excite it here, the only decay it can do is back to the state here, via emitting a sigma plus polarized photon. And now if I calculate what I would expect that there's, for the one propagation direction, a large overlap, so the photon should be well covered in the direction of propagation, let's say in the positive direction, whereas there's almost no overlap with the other direction because that was locally sigma minus polarized. And so we would expect an asymmetric emission into the waveguide modes. So this is the measurement outcome. So here on this axis, we denote the Zeeman excited state. So for example, MF plus 4. And here is a measure for how much light goes to the left and to the right. So that's the directionality, which is defined here. And indeed, what we experimentally observe is if we excite the atom to that state and look at the decay, then most of the light goes out to, let's say, the right direction. Whereas if I'm preparing the atom here, most light goes out to the left. And then I can also realize intermediate situations. For example, if I prepare the atom in that excited state here, then it has in total 3 decay channels. One will be sigma plus, one sigma minus, and one pi polarized light. And there we expect that the directionality is reduced. And this is also indeed what we measure. So to summarize, what we can realize here is we can control the routing of photons into the fiber via the atomic state of the atom. Okay. So that was a confirmation that this chiral nature of the waveguide modes behave as we expect. And the next thing we wanted to do is we wanted to implement application of these chiral photons. And the application we chose is an optical isolator. So we want to build a device where light propagation in one direction is different from the light propagation in the other direction. The way how we do that is summarized here. So again, we want to build up on this connection of the local polarization and the propagation direction. But this is not all what we need. We need something in addition, and that is we need to induce an emitter which has a different absorption probability for a sigma plus or a sigma minus polarized photon. And the way how we can do this is twofold. So let's assume there's such a level scheme here. So the atom can be initially in the ground state, and the coupling to this state via sigma plus transitions should be somehow different than to this transition. And there are 2 ways to realize that. One way is we choose this ground state such that the Clebsch-Gordon coefficients are intrinsically different. And another option is we apply a magnetic field and then introduce a detuning and thereby realize a different coupling to these two states. So this is the ingredients that we require for our optical isolator idea. And in principle, if we just, so to say, focus on the first aspect, this concept for an optical isolator would be working without any magnetic field, because that's an OR connection between the two. You can have both, but one criterion would be already enough. Okay, so how can we realize that? So we used again our capability of trapping cesium atoms close to the nanofiber, and now we prepared all cesium atoms trapped close to the fiber in the outermost state of the F=4 ground state manifold. And for that state here, the coupling via sigma plus transition to MF=5 in the excited state is 45 times stronger than to that state over here. That means we have indeed a really strong imbalance between sigma plus and sigma minus transitions already given by the Clebsch-Gordon coefficients. And for technical reasons, we also apply a small magnetic field. That's due to the fact that otherwise the spin state is not preserved, but we get spin flips. So we have to apply a small magnetic field. But the main effect will be from the difference in the Clebsch-Gordons. And so what we expect is, for one propagation direction, we will couple strongly to the atoms which are close to the fiber. And okay, due to the relatively weak coupling that we have in our system compared to other systems we heard about, most light will be just scattered out, and thereby the transmission will be reduced. Whereas if I send light in the other direction, the atoms will just not couple to the light field, and most light will propagate through the fiber without absorption. So that's the experimental results here for the two situations. So here's a measurement of the transmission. And indeed, we see the expected behavior. We see a strongly asymmetric transmission. For the one propagation direction, we get about 15% roughly, whereas in the other direction, we get on the order of 80% transmission. So indeed, we can see the isolator behavior as expected. And this is corresponding to an isolation of about 8 dB at forward transmission of about 80%. And the measurement here was conducted with about 30 atoms. So 30 atoms were enough to make this optical isolator. But now, in the next step, we wanted to also be able to tune the optical isolation. And the way how we do that is, so we again take advantage of the particular polarization structure of the guided modes. So here's an illustration. So here's again the nanofiber. We send in light from the left, and this light field should be linearly polarized along the x-axis. And this thing is an intensity plot. And now, if you look at the z component, which is the cause of the chiral nature of the photons, actually that has a strong dependence of the transversal position where I'm actually looking at this property. So exactly on this axis here, there's a strong z component and also therefore a strong ellipticity or a strong chiral aspect of the photons. However, on the other axis, so in that direction here, there's still an evanescent field, but the z component actually is exactly 0. And for that reason, we expect that there should be no chiral behavior. So the way we can tune the isolation is we just can turn the polarization of the incoming light field with respect to the plane where the atoms are trapped, and thereby we can tune, so to say, how much chirality we have. So this is what we also did experimentally. So on that axis here, we have the polarization angle between the two planes. And here's the transmission for forward and backward direction. And these 2 points here are the points which we just saw on the last on the last slide. And indeed, so now if I turn the incoming polarization, I can switch from a strongly asymmetric transmission to a fully symmetric transmission where just both light fields are going through. And the reason here that this is actually almost transmission 1 is we have applied a small magnetic field, therefore the light, which is then here pi polarized, is coupling to the tuned state and therefore not coupled and then just transmitted. If we wouldn't need to apply that magnetic field for the stabilization of the Zeeman state, then this would be at a finite value, but it would be still symmetric. Okay, so we can do both, so we can really tune the isolation. And one more word about what is limiting the transmission actually here. This is related to the fact that we don't have perfect overlap with sigma plus polarized light, but in the end, the light is only 92%, for example, sigma plus, and the remaining 8% are actually sigma minus polarized. So also for the backward propagating light, there will be some coupling to the stronger transition. Okay, so we realized the tunable integrated optical isolator with about 30 atoms. But now we wanted to go further, and we also wanted to try to do it with just a single atom. And so as we have a relatively small coupling of these atoms to our optical nanofibers, we have to increase the coupling strength in order to get a significant effect of a single atom to the light field. And the way how we do that is we use our whispering gallery mode resonator. Thereby we can enhance the coupling strength to the atom. And so now the system we have is we have that nanofiber, we have a bottle resonator. This nanofiber can be used to couple light in and out of the resonator. And the atom is now coupling to the evanescent field, which is circulating around here. And it's important to note that also in these structures here, we have chiral photons. And that is due to the fact that this is also relying on, total internal reflection. Therefore, we get a strong decay of the electric field away from the fiber surface. Therefore, we have that transverse gradient that I was talking about initially that we need to get the Z component. So therefore, in these structures here, we have exactly the same chiral physics that I explained for the nanofibers before. So essentially what will happen is if I send in light from here, it will couple like that, and I get locally, for example, sigma plus polarization. Whereas now if I send it in from the other side, this will be, that was sigma minus and that was sigma plus polarization. So I can choose by the port that I'm using which to which transition of the atom I'm actually talking to. Okay, so the two cases that we have then are summarized here. So if we send in light in the forward direction, the light is actually fully entering the resonator, and we set the coupling strength between the coupling fiber and the wavelet and the resonator such that we are under critical coupling, so almost all light will be dissipated in the resonator and no light will be transmitted. And the transition driven in this situation is this weakly coupled transition, so therefore this is as if the atom is just not there. On the contrary, if I'm sending in light from the other direction, we are talking to this strong transition of the atom. And what happens then, as we are in the strong coupling regime, we get a vacuum Rabi splitting of the transmission spectrum. So therefore, the light is prevented from entering the resonator, and therefore it's just transmitted along the fiber. So that is the mechanism which is here, the physical idea behind getting a different transmission through that fiber in that direction and in that direction. All right, so here's a more systematic study. So here's a simulation of the fiber resonator coupling strength and the transmission that we get in the forward and in the backward direction. So in the forward direction, where we expect no coupling, I can, for example, at this particular point, get to the critical coupling condition and no light is transmitted. But then at the same time, the backward propagating light will be transmitted due to that strong coupling. And in the end, this will lead to a very large isolation, which is actually diverging here, so which is in the calculations even infinity, due to the fact that this transmission goes exactly to zero. Okay, and so that's a simulation. We did the measurement exactly here. So these 2 points are measured data points. And So we see indeed also in this system we can get with a single atom in one direction transmission of about 70 or 75%, whereas in the other direction we have almost zero transmission. That means also for that case we have that non-reciprocal behavior mediated by a single atom only. And in order to confirm that this was indeed only a single atom, what we measured was a G2 correlation function. So we took the port where still light comes out. So we sent light in the backward direction and did a G2 measurement here. And the signal here indicates that there's just a single atom. The reason that this is not going to lower values than what we have here is, so it's the excitation light field is co-propagating in the same direction like where we detect or where we measure the G2 function. And therefore, there's always some of the excitation light also going here, which is in the end reducing the contrast of the G2 function measurement. But yeah, so still if you do the calculation, you can see that this is exactly the, we put in all our system parameters and then we make a kind of based on these known system parameters, calculation which G2 function we would expect, and this is exactly what we get in the experiment, and therefore we are confident that indeed the measurement was only done with a single atom. Okay, so the isolation we got here was about 12 dB, and yeah, that already brings me to the end of my talk. So to summarize, it's important to keep in mind that in nanophotonic structures there can be unconventional polarizations, and in particular this link between the local polarization and the propagation direction, which is just arising from the strong confinement in these structures. And what we also showed is we could excite waveguide modes and control this by the excited states of cold cesium atoms coupled to the waveguide. And in the second experiment, we showed an application of this chiral nature of the photons that we have in the system. So we built an optical isolator where the internal states of a few atoms have controlled the operation mode of the optical isolator. Moreover, we showed that it's also working with just a single atom, which in principle opens up the possibility to do new things like preparing the atoms in superposition states, for example. And I didn't quote any numbers, but actually there are large efforts to build integrated optical isolators also by other means, for example, using time modulation or using nonlinear effects. And also, if you compare the numbers that we heard about in the talk with what other solid-state implementations have, our implementation is actually also quite compatible, so we get compatible numbers to other systems. So now a few words about the prospects of our work. So we are convinced that this chiral nature of photons is quite an important new idea, and that there are many follow-up ideas that we can build up on this concept. One thing is about one idea we will hear later. So there's been already a couple of works in the group of Peter Zoller and Hannes Pichler will talk more about that. So what you can do is, so if you have chiral coupling, so quantum emitters which can mostly emit to the right, for example, and not too much to the left, and you build a chain of these atoms all coupled strongly to the waveguide, then what happens is you can you can drive the system dissipatively into a state where these atoms are teaming up as dimers, and so the dimers are always entangled, but so there's a big product state always of two dimers, which is building up just by continuously driving that system. And a second aspect is that there's a couple of quantum information protocols which now get available thanks to this physics. A few were already mentioned by Peter Loder in his talk, and actually I think this list of citations is probably pretty incomplete from what I heard yesterday. So we are convinced that this chiral coupling can be used for many protocols as well. Second aspect is we can also actually look at the effect on the external degree of freedom, which is arising from this asymmetric emission. And we have one work where we put an emitter close to a waveguide, and what we observe is so not only the emission into the waveguide modes, but also the free space modes are in general not symmetric if you emit the right polarization. So the total emission into the two half spaces are actually imbalanced, which in the end leads to a force on the atoms which are emitting sigma polarized light, for example, close to that structure, which is then leading to a force which moves the atom parallel to the waveguide surface. And so the last aspect is in a more applied concept. So the chiral character photons that we discussed in the talk might also be used for several experiments on a chip. So for example, this idea of routing photons in a waveguide could be implemented on a chip such that I have one waveguide here where there's an emitter sitting on top of it, and then if I supply here sigma plus or sigma minus polarized light, that should be either scattered to the left or to the right. Or you can also realize the optical dye that we realized exactly in a waveguide structure, just using exactly the same principle. And the next step to do would be also to realize not only isolators but optical circulators. So the way to do that would be we add a second fiber to that whispering gallery mode resonator setup. In this case, the light would not just be dissipated as it was under critical coupling, but the light would be actually coming out here. Or if the atom is in the other state, it goes through here. And if you do things right, you can actually realize a circulator capability where each signal is just routed to the next consecutive port. And ideally, you could do that with just a single atom. Actually, so from what we have achieved until now, we are confident that in our system, for example, it should be possible to also realize an optical circulator. Okay, so that are the people who contributed to this work. So all these things have been done in the group of Arno Rauschenbeutel, which is photographed here. The people who worked on these particular experiments are highlighted in red. And I also like to thank our funding agencies, and I'd like to thank you for your attention.
So you said the overlap with the circular polarization is about 92% in
Yes.
the case of fiber.
Yes.
How about in the photoresonator?
I think it's 97%, so it's even a bit larger.
And is there a way to improve it towards 100%?
Only asymptotically, so if the refractive index contrast is getting larger, then this is also getting larger. And actually, so even for our structures, if you are not staying outside of the waveguide but you go into the waveguide, then there's a point where the absolute value of the Z and the, for example, the X component are exactly the same values, so there you have perfect circularity. But as we can't move the atoms into the piece of glass, we can't take advantage of that yet. Yes, so yeah, indeed. So here it's the same reasons behind that. So this directionality here is limited by the finite ellipticity or circularity of the local mode. And if we could increase that, we could also increase the directionality. So we have another paper where we got a ratio of 40:1. Actually, okay, so it's more complex. So one aspect is just to increase the circularity, okay. But actually, it turns out that you can always find emitted polarization, which is even for this structure orthogonal to both modes propagating one direction. This will in total not lead to even more coupling into the waveguide, so it will actually decrease the coupling to the waveguide, but you can maximize the directionality with that. But it's not so easy to so to say, get the atom to emit exactly this particular superposition of polarizations that you would need to be orthogonal to both modes.
So I guess to do this isolator, you need this non-reciprocal propagation. You somehow have to do something that kind of breaks time reversal.
Yes.
Right? And so when the magnetic field is on, then
Yeah.
that does it. But without a magnetic field, how do I think about it? Is the magnetic moment of the atom itself?
Exactly. So this is what we think is the reason, and therefore the atom needs to be spin polarized. So the spin projection has to be unequal from 0, because exactly then the coupling to sigma plus and sigma minus is always the same or symmetric. Whereas if you pump it to one of the outermost states, then it gets asymmetric. It has a spin, and then the diode works.
Actually, I have a question regarding this bottle resonator.
Yes.
If you want to go single atom, then you have to increase your finesse.
These measurements I showed were single atom.
So then
Yeah.
that will come as expensive, decreasing your bandwidth.
Yeah, okay. Yeah, so I mean, that's the problem of that particular isolator. So that's a resonant isolator, right? So, and therefore this concept of isolator always suffers from bandwidth arguments, whereas a conventional optical isolator that you buy in the lab is anyway working in a dispersive regime, and therefore small detunings. I mean, if few megahertz detunings compared to the terahertz that you are away from the resonance of this material don't come into play. In our case, it's different, as we work on resonance. So this is about the technical principle which is behind implementing that isolator. However, I mean, at the same time, you could also implement it in a dispersive way. So we got a non-reciprocal transmission, but nothing prevents you from getting a non-reciprocal phase shift in the system by detuning it. And then it's only a question how large is that phase shift. But if the coupling between light and...
That would also, the phase would also decrease as you...
Yeah. I mean, this is why these optical isolators are so large. I mean, they have Tesla fields and they are really long because the phase shift is really small, especially the phase shift difference that they get. And therefore, it's a big technical challenge to make an integrated small isolator. That means you need to get a large phase shift over a small distance. Our attempt was not to beat the optical isolator industry, but more to focus that we can show it with single quantum emitters.
Okay, one last question.
Just a quick technical question. So we saw in the first two talks that there's a lot of possibilities in this nano-fabricating and so on. I'm just wondering if there's any efforts in your group to do some additional fabrications on top of these fibers instead of, I think most of the stuff is by stretching or something.
Yeah, so the production of the two systems that we have is relatively low tech, so we don't have any lithographic fabrication facilities. They are both, so the whispering gallery mode resonator and the tapered fiber are done with heat and pull process. And so one could now also try to improve these, or like further modify these structures by, for example, if you have the fiber, drill holes in it in the right way in order to get a cavity. So we did some effort on that, but so our fabrication facilities are not as excellent as we would hope for. So we saw that as we tried that, we introduced always more and more absorption of the structure, which in the end easily led to burning of the fibers. And we still have to, I mean, in order to get the atoms here, we have to send in milliwatt trapping light fields through the fiber. So even small absorption is already a problem. There are other tricks. I mean, what we did, so we have a structure where we have a tapered fiber and a commercially available fiber back gratings outside. So in that, by these means, we can also get to a single atom strong coupling in these tapered fibers if we enhance the confinement using fiber back gratings on the outside.